Now you have the next case, case number 5, where the water table is below the ground level. We started the discussion with a dry backfill, and then we had another case where you had the water table at the ground level, and now you have the retaining wall here, you have the ground level here, and the water table is somewhere in between the ground level and the base. Let's say it's at a height h1 from the ground level and h2 from the base. So in that case, the pressure distribution diagram, of course, starts at 0 from the top and varies linearly with height h and reaches a value of Ka gamma h1 at the interface. So you have the triangular distribution here with the base width of Ka gamma h1, where gamma is the unit weight of the soil above the water table and h1 is the height of the soil above the water table. Now, beyond this level, which means beyond the interface, gamma into h1 will act as a surcharge, which means at level, interface level, gamma multiplied by h1 will be the surcharge load. So that surcharge load will represent a pressure distribution diagram like this, Ka into gamma into h1. It's quite similar to the Ka into Q we discussed earlier. Plus, we have another triangle which starts at the interface and varies linearly with h2 height to reach a value of Ka gamma dash h2, which means this portion takes into account the submerged density and the height h2. Of course, this is one big trapezium. It is divided into one triangle, one rectangle, and another triangle. Plus, you have gamma W into h2 like this. It starts at the interface because the water table is present at the interface. You have 0 value there, and it linearly increases with h2 height and reaches a value of gamma W into h2. In short, you have 4 different figures, 3 triangles and 1 rectangle defining the lateral earth pressure distribution. So PA, the value, will be sum of areas of rectangle and these 3 triangles, and PA will be acting the combined center of gravity of all these 4 figures. Now the next case is a case where you have a layered backfill, which means you have 2 separate soil strata, 2 or more than 2. Now I have marked h1 here and I have marked h2 here, which means I have a soil of unit weight gamma 1 here for height h1, and I have a different soil with a different gamma 1 at height h2. One thing that we need to take care is that when the soil is different, you have different unit weights, you have different angle of internal friction. So since angle of internal friction phi varies, Ka also varies, which means layer number 1 will have a Ka value Ka1 and layer number 2 will have another Ka value, let's say Ka2. So the distribution diagram again starts with 0 at the top, linearly varies up to the interface, reaching a value of Ka1 gamma 1 h1, gamma 1 being the unit weight of the soil in the layer 1 and h1 being the height. Now just below that, like we discussed earlier, gamma 1 h1 will act as a surcharge. So you have a rectangle here where gamma 1 h1 acts as a surcharge, but you need to take care of the Ka value here. The soil here is soil number 2. So you have Ka into 2, Ka2 multiplied by gamma 1 h1. So earlier you had Ka1 gamma 1 h1 at the interface. Just beneath that you have Ka2 gamma 1 h1 acting as a surcharge. So in short, at the interface, just above the interface you have Ka1 and just below the interface you have Ka2. Plus you have another triangle, starts at 0 there, and reaches Ka2 gamma 2 H2 at the bottom, which means gamma 2 H2 is 0 at this level, and gamma 2 H2 has a value of gamma 2 H2 at this level. So it linearly increases with respect to H2 height. So the first triangle was about H1 heights variation. The rectangle is about the surcharge load gamma 1 H1 offered on each soil layer 2, and the third triangle is about the linear variation in the layer 2. Now, I have found students getting confused about this distribution. That's why I wanted to stress that at the interface, just above the interface, you have Ka1, and just below the interface, you have Ka2. If you still have some clarifications required, we'll discuss that when the numerical problems are discussed. The next is Rankine's earth pressure theory for clay. Now, while defining the assumptions, we had defined the soil to be cohesionless. But when the soil is cohesive, you need some modifications for the equation. Now let's consider a retaining wall with a height Z instead of H. And let's try to define the active pressure here. At any depth Z below the ground level, the active pressure, when you have C5 soil, cohesive frictional soil, is defined by Ka gamma Z minus 2Z root Ka. Z is the same H that we used for the earlier case, just for us to discriminate between clay soil and sandy soil. I have marked this at Z. Okay, gamma Z minus 2Z root Ka, where C is the cohesion of soil, and based on that equation, you can see that when you put Z is equal to 0, which is at the ground level, the active pressure will be negative 2Z root Ka, right? When Z is equal to 0, the value will be minus 2Z root Ka, which means the negative sign indicates pulling or tensile force. In short, the distribution would be like this, with a value of minus 2Z root Ka at the top, and a 0 value at the middle, and a value of K gamma Z minus 2Z root Ka at the bottom, like this. Now, assume a case where you have the active pressure as 0, which means Ka gamma Z minus 2Z root Ka is equal to 0. That is nothing but this point, right? The point where the negative sign changes to the positive sign. It's quite similar to the point of contraflexure that you've studied in the bending moment distribution of the beams. Now, when you solve this equation, K gamma Z is equal to 2Z root Ka, or Z will be equal to 2C by gamma root Ka. Now, I can call this Z as Zc, which is called the depth of tensile crack. Now, that depth of tensile crack is marked in this figure, Zc. That's the depth from the ground level at which the soil is in tension, which means you have the negative sign here. So, you have Z minus Zc beneath that. Now, when I take twice the depth of tensile crack, which means 2 times Zc, I'll get a height called as the critical height of unsupported vertical cut, which means Hc, critical height of unsupported vertical cut, is equal to twice Zc. In short, at level Hc, the negative triangle gets cancelled out with the positive triangle, because you have two triangles of the same area with the same angle of opposite angles with two different signs, so that gets cancelled out, and it's called the critical height of unsupported vertical cut. Now, one thing you need to note is that for pure clay, Ka will be equal to 1, which means you have 2C here and you have gamma Z minus 2C here. Now, the passive case for clay soil, the equation is for any depth Z, you define it as Kp gamma Z plus 2Z root Kp. So two differences, Ka gets replaced by Kp and the negative gets replaced by positive. And for the same reason, you don't have the tensile area there. Instead, you have a magnitude of 20 root Kp. So you don't have 0, you don't have negative, you have a positive value, 20 root Kp at the top, and Kp gamma is at plus 20 root Kp at the bottom. And again, for pure clay, Kp will be equal to 1.